Welcome to our QAOA Masterclass brought to you by qubit-lab.ch. This is a practical overview of QAOA for finance-style constrained optimization. We will cover QUBO and Ising formulation, cost and mixer unitaries, constraint handling, and parameter tuning. I will also share implementation tips, common pitfalls, and what to report so results look credible. Here is what we will do. First, where QAOA fits and why it is useful. Then, QUBO basics and a toy QUBO example. Next, the cost layer from QUBO to cost Hamiltonian to cost unitary, including a calculation and a circuit. Then the mixer layer, starting with the standard mixer and then other types. After that, multi-position unit encoding for both the cost layer and the mixer layer. Finally, practical tips, including parameter optimization, pitfalls, and reporting. What is QAOA good for? It is a practical approach for combinatorial optimization under constraints, often written as a QUBO or Ising model when brute force becomes infeasible. In finance, this shows up in portfolio allocation with budgets, cardinality, and lot sizes. It also shows up in turnover-aware rebalancing, execution scheduling, and balance sheet allocation. The common pattern is discrete decisions plus constraints. Finance fits well because many real decisions are binary. Select or not select, trade or not trade. And these map naturally to a QUBO objective. The goal is to generate high-quality feasible samples, not just a theoretical minimum. Now a quick reality check on hardware. We are currently in the NISQ era, noisy intermediate scale quantum. Devices operate without fault tolerance, so circuits must be short and noise is significant. That is why we focus on hybrid algorithms, quantum circuits inside a classical loop. Fault-tolerant quantum computing is the longer-term goal based on logical qubits and active error correction. Early fault-tolerant capability may emerge in the late 2020s. Broader, commercially meaningful systems are more likely in the early 3030s. So for now, QAOA is interesting because it is designed for the NISQ setting. So why do people use QAOA? Because it is one of the most practical quantum optimization candidates for near-term hardware. It is hybrid by design, a quantum circuit plus a classical optimizer loop. And the core idea is simple. We alternate a cost unitary that encodes the objective and a mixer unitary that enables interference and exploration. Gamma and beta are interpretable knobs that tune the search. And mixers are extensible, so we can sometimes encode constraints in the mixer instead of relying only on penalties. QAOA is not magic speedup. It is a structured variational heuristic that can produce high-quality samples. Here is the workflow in one slide. First, define the problem as a QUBO, a cost function over bit strings. Each bit string is one candidate solution, and lower cost is better. Second, prepare a uniform superposition, so we start with all candidates at once. Third, apply the cost layer. It adds cost-dependent phases. Fourth, apply the mixer layer. This recombines amplitudes and enables interference, reshaping the probability distribution. Fifth, measure many shots, estimate expected cost, and update gamma and beta with a classical optimizer. Finally, after training, sample the circuit and keep the best feasible bit string you observe. We repeat cost and mixer p times, where p is the number of QAOA layers. This is the circuit template. We apply H gates to prepare an equal superposition. Then, for each layer, we apply UC with gamma, then UM with beta. After p layers, we measure all qubits to get classical bits. The essence is straightforward. The cost layer encodes the objective as phase shifts across the candidate solutions in superposition. The mixer defines how you explore and turns those phase shifts into interference, which amplifies solutions with lower QUBO cost. Now we formalize the optimization problem. We formulate portfolio optimization as a QUBO function, quadratic unconstrained binary optimization. The QUBO defines the cost function we minimize. And encoding a problem as a QUBO is not automatic. It requires careful design and tuning. There is also a key constraint choice. Either enforce constraints via penalties in the QUBO, or design the mixer so you never leave feasible states. Let's make this concrete with a toy example. We have 4 investment opportunities. Each is available only in a fixed $1 million ticket size. We want exactly $2 million invested, so we must pick exactly 2 deals. The decision vector x is a vector of zeros and ones. Return is R transpose x. Risk is x transpose qx, where q is the covariance matrix, and the constraint is that the sum of x equals 2. So the QUBO is negative return plus lambda times risk plus a times a squared penalty enforcing the constraint. Lambda sets risk aversion, assets how strongly we enforce the budget constraint. Now we translate this QUBO into a cost Hamiltonian and a cost unitary. Now let's look at how to derive a unitary from a Hamiltonian using so-called generators. This slide is the key bridge from our math model to an actual circuit gate. In QAOA, we write the problem as a Hamiltonian, meaning a sum of simple terms built from Pauli operators. To turn such a term into a gate, we apply one rule. We exponentiate it. That gives us a unitary. And the parameter alpha controls how strongly we apply that term. A useful intuition is the small angle view. For very small alpha, the unitary looks like identity, plus a small change in the direction of the generator. That is why we call it a generator term. 2 practical details matter. First, the minus I in the exponent. This ensures the result is a valid quantum gate, meaning it preserves probability as long as the generator is Hermitian, which is the case for Pauli operators and Pauli strings. Second, the factor 1/2 you sometimes see in gate definitions. Quantum gate libraries define rotation gates using an angle parameter theta. So the angle you pass to a gate like Rx is typically 2 times the alpha used in the algorithm expression. That is why we use the mapping theta equals 2 alpha. At the bottom are the identities we will use as lookup rules. X rotations create mixing, Z rotations create relative phase, and Z rotations create a coupled phase between qubits. In the next slides, we apply these mappings to convert our QUBO cost into a cost Hamiltonian, and then into the cost layer unitary in circuit form. We now build the cost layer. Step 1. Start from the QUBO cost function. Step 2. Define a cost Hamiltonian so that each basis state gets an energy equal to its cost. In other words, when the Hamiltonian acts on a basis state, it reproduces the same state and attaches its cost as a multiplier. To implement this on a circuit, we rewrite the binary QUBO in 0 and 1 into an Ising form in spin variables, meaning -1 and +1, and express it using Pauli-Z and ZZ terms. Step 3. Define the cost unitary from that Hamiltonian. This unitary is diagonal, so it adds cost-dependent phases. Practically, we turn each Hamiltonian term into rotation gates using the generator identities from the previous slide. Those phases matter because the mixer can convert them into constructive and destructive interference. Here is the key mapping step. We switch to -1 and +1 spins because the Pauli-Z measurement outcomes are -1 and +1. We want to represent the same cost function using Z and ZZ terms, so we can build a unitary. In the computational Z basis, Z acting on 0 gives +1 and Z acting on 1 gives -1. So the natural variable is a spin S in -1 +1. We use the term spin for historical reasons. The formalism was developed for electron spins. In QAOA, it is simply a ±1 variable. No physical electron spin is required. We map a binary variable x to a spin using x equals 1 minus s over 2. Equivalently, x equals 1 minus z over 2. This converts the QUBO into a so-called Ising form with only zi and zizj terms. After substitution and expansion, the cost Hamiltonian takes the standard Ising form. It is a sum of single qubit terms hi, zi plus a sum of pair terms ji, j, zi, zj plus a constant. The constant is an energy offset you can ignore for optimization. It does not change which bit string is optimal. So the output of this step is the list of H values and J values. Now we turn the Hamiltonian into a circuit. We define UC of gamma as the exponential of minus I times gamma times HC. Because all Z and ZZ terms commute, the exponential factorizes into a product of simple exponentials. We also ignore the global phase from the constant offset. Each HIZI term becomes an RZ rotation, with angle 2 times gamma times HI. Each JIJZIZJ term becomes an RZZ rotation with angle 2 times gamma times JIJ. Next, we make an explicit example and compute the actual angles. These are our toy inputs. The expected returns per asset are as shown on the slide. The covariance matrix Q is shown below. We set lambda to 1 and A to 5. From this we compute H and J and therefore the rotation angles. Single terms map to RZ with angle 2 gamma HI. Pair terms map to RZZ with angle 2 gamma JIJ. One quick note. The penalty term dominates the pair couplings JIJ here because A is set to strongly enforce the constraint. Here is the cost layer circuit. Apply RZ rotations for the H terms. Apply RZZ rotations for the J terms. Because Z and ZZ terms commute, the order does not matter mathematically. So you can reorder gates to match connectivity and reduce depth. The takeaway is simple. Once you have H and J, the cost layer is fully specified. Now that the cost layer is fully specified, we move to the mixer. The cost layer encodes the objective by adding cost-dependent phase differences across the candidate solutions in superposition. But phases alone do not change what we measure. The mixer is the step that turns those phase differences into changed sampling probabilities through interference. In other words, it converts the objective information into a bias toward better bit strings. The mixer also provides controlled exploration. It pushes probability mass toward nearby candidate solutions, so the algorithm can move away from poor local patterns instead of getting stuck. Conceptually, building a mixer is simple. First, decide what moves are allowed. This is your mixer generator. Second, turn it into a unitary with a parameter beta that controls the mixing strength. For small beta, the action is a gentle nudge, not a full bit flip. In the next slide, we apply this to the standard choice, independent bit flips, which leads to the standard RX mixer used in many baseline QAOA implementations. Let's build a standard RX mixer layer. The standard mixer Hamiltonian is HM equals the sum of Xi over all qubits. The mixer unitary is UM of beta, the exponential of minus I beta HM. Since the Xi terms commute, the unitary factorizes into single qubit operations. Each term exp of minus I beta x is equivalent to Rx with angle 2 beta. So the standard mixer is Rx of 2 beta on every qubit. Practical note. This mixer does not preserve the PIC exactly to constraint by itself. With penalties, it can work as a baseline. Constraint-preserving mixers can be more efficient. Here is the bigger idea. Mixers are a design choice. They define allowed moves. Standard Rx mixer flips bits independently. Weighted Rx biases exploration by flipping some variables more strongly. For PIC exactly k, an XY type mixer preserves Hamming weight by swapping a 1 and a 0. This keeps you in the feasible subspace. Graph-aware mixers restrict mixing to allowed edges, encoding structure and reducing wasted exploration. You can also combine mixers or vary them by depth. So far, each asset was 1 bit. Now we move to discrete position sizes using registers. Binary selection is easy, but real portfolios need discrete position sizes. So we encode each position as a small integer register, which turns the problem into a larger QUBO over more binary variables. In the 1-bit case, We have 4 assets and 1 qubit per asset, so 4 qubits total. In the 3-bit case, we still have 4 assets, but we allow 8 discrete position units, so each xi ranges from 0 to 7. That means 3 qubits per asset, so 12 qubits total. We encode each integer xi with 3 bits as qi0 plus 2qi, 1 plus 4qi2. After substitution, C3 becomes a standard QUBO over 12 binary variables. Then the bit-to-spin mapping is unchanged. Each q becomes 1 minus z over 2, so the derivation of hc and uc follows the same steps. But 3-bit encoding yields more terms, more qubits and more zz couplings because each x expands into 3 bits. The cost layer mapping stays the same. What changes next is the mixer. Now the mixer for registers. Assume 2 assets, meaning 2 registers, and 2 qubits per register. Each register encodes an integer level from 0 to 3. We define a single register step, Hamiltonian, that connects neighboring levels on the chain from 0 to 3. Then the full mixer Hamiltonian is the sum of that same operator acting on each register. These per register terms act on disjoint qubits, so they commute. Therefore, the mixer unitary factorizes across assets, and each register unitary can be implemented using a Suzuki-Trotter product of the edge mixers. Here is the concrete circuit view. For each register, the step unitary is approximated with a Suzuki-Trotter product. One step applies 3 edge mixers in sequence, for the edges 0 to 1, 1 to 2, and 2 to 3. Because registers are separate, we apply the same register block in parallel across assets. There are no cross-register gates in this mixer. To improve the approximation, repeat the edge sequence r times using smaller angles, beta over r. Better approximation, more depth. Here, some implementation tricks to simplify the mixer layer. Cost layer encoding and mixer should be chosen together. Gray code makes neighboring integer levels differ by 1 bit, which can simplify local moves. But decoding can be nonlinear, which can complicate the cost mapping. Domain wall encoding makes neighbor moves very natural, but it uses more qubits. A sum-preserving transfer mixer moves 1 unit from one asset to another, while keeping the total constant. This can enforce feasibility and reduce wasted exploration. So there is no one best choice. You choose what matches constraints, circuit depth, and hardware connectivity. Here are some practical decision rules. If strict feasibility matters, use a constraint-preserving mixer. For pick exactly k, use an XY or swap-style mixer. For fixed total units in multi-position encoding, use a transfer mixer. If strict feasibility is not required, start with penalties plus a simple mixer, like standard Rx. Then consider how tight constraints are. If the feasible subspace is small, constraint-preserving mixing can save many shots. Finally, weigh complexity against hardware limits. Start simple for a baseline, then upgrade the mixer when efficiency matters. Now we tune parameters. We need to optimize gamma and beta. On noisy hardware, gradient-free optimizers are often robust, such as SPSA or Cobila. On simulators, gradient-based methods can work well. In practice, expect local minima, so use multi-start. A good trick is warm start by depth. Optimize 1 layer. Then use that solution as the initial point for 2 layers, and so on. Also use as shots schedule. Low shots early, higher shots near convergence. Here, some common pitfalls. Penalty too low gives infeasible solutions that look good on objective value. Penalty too high makes the landscape stiff and mixing ineffective. A mismatch between mixer and constraints wastes shots. Shot noise can destabilize optimization and trap you in local minima. Fixes include sweeping the penalty, using constraint-preserving mixers, using multi-start, warm start, and noise-tolerant optimizers. Also, do not report only the expected value. You must look at feasibility and best sample quality. and you should repeat across seeds to check robustness. And finally, what should you report so results are credible? Report feasibility rate, meaning the fraction of samples that satisfy constraints. Report best and median feasible sample score, not only expected value. Report robustness by repeating across a few random seeds and reporting the spread. Optionally, compare to a simple baseline such as random sampling or a greedy heuristic. And always state your compute budget. Depth P, number of shots, and optimizer iterations. That makes results reproducible and interpretable. So with that, we got to the end of this video on QAOA. Many thanks for your time. I hope you found this QAOA Masterclass interesting and useful. Some parts were quite technical, but I aim to keep it practical. If you want to explore more, visit qubit-lab.ch. And if you have feedback, questions, or suggestions, feel free to email me. I am more than happy to hear your thoughts and discuss. Have a great day.